Okay, so first thing is we still need to go over the back page of this homework 1. We've gone through all of homework 2. Homework 3 we've covered. It said don't do this, and then it said do this later on. There was a little mistake on that portion. We did change stuff. We have homework number 4. I didn't finish this portion, so we need to go and look at that. But homework 5, that's where we're at. Homework number 5. Okay. And again, I need to kind of update our homeworks just so that way if you miss something, by any chance, the answer key can be posted on D2L for you. Question number 1. Question number 1 is really actually kind of hard to explain or go over. Like, it doesn't give us a lot of info. It should have. Question number 1 is there are 3 marbles on the table. So imagine 3 marbles on your table. Now, all 3 marbles are going to fall from the same table. That means the same vertical height. You can see that. But all 3 marbles fall at different locations. Marble A, marble B, and marble C. What they did not tell you is these 3 marbles fell off of the table at the same time. I think that was crucial information that they should have said. Now, when they fell off of the table at the same time, from the same height, all 3 of them will land on the ground at the same time. And that kind of goes back to that little cartoon notes that I was showing you that's on D2L for you to fill in, kind of like Galileo. When he was tossing those cannonballs off of the, Leaning Tower of Pisa, one was just dropped and one was thrown out at the same time. It didn't matter if it had a horizontal velocity or not. The moment that they are released, gravity is pulling on them, and gravity pulls on all objects the same. Let's move on to question number 2. So on question 2 over here, it says there's a ball that rolls off of a table. Okay, so here's my table, and here's my ball. It says that this ball has a velocity of 2 meters per second. This is actually the lab that you are going to do in about 3 weeks, maybe 4 weeks, you and your lab partners in class. Now, they actually told me the distance of the vertical, which is 1 meter. And what you're going to do is you're going to come in here and you're going to find that vertical meter of those lab tables. You're going to find that distance here. You're going to find the velocity of the marble before it leaves the table. Now, when it leaves the table, you can tell that it's going to form this trajectory of a parabolic path, a parabola. Now, when we have a parabola and when an object's in the air, we call that a free fall question. That means that not only does it have horizontal, it also has vertical components. Because of that, we do the X and Y T-chart. This is still called kinematics, but it's in the X and Y component at the same time. In the X direction, we have Vx, Dx, and T, just like those cartoon notes that you are going to fill in later. In the Y component, we have VIY, VFY, DY, T, and A. Now, when we fill in the blanks, we can see the velocity horizontally, they told me right here, is 2 meters per second. The distance that this ball is going to land is a question mark, and the T was never given to me. The vertical component of your homework, number 5, is the VI. When it's moving in a vertical direction, the VI, we stated, is always 0. But VF was not given to me. The DY was 1 meter. T was not given to me. And we know the moment that gravity's pulling on it, it's 9.81 meters per second squared for acceleration. I'm actually trying to solve a variable over here in the x component, but I don't have enough information. So I'm going to solve on the y side, this t, plug it in over here, and then I can solve for what I actually need. So it's a two-step problem. D equals 1/2 AT squared. Do you remember that we did this equation, but we also had a VI and a T in front of this? Now I'm going to ignore it because VI is always 0. Who cares about that? Ignore the 0. Distance is 1 meter times 0.5 times gravity, multiply it by T squared. I need to cancel this. When I multiply those two numbers, it's 4.905. Divide by 4.905. I'm going to end up over here with a variable. My variable on this side comes out to T squared of 0.204. Not my answer because I do need to square root it. So I'm going to do a little square root thing here. T, again, is still not my answer. It's just the T of 0.452 or 0.45. Or maybe you just rounded it to 0.5. That works also. I'm going to plug that in over here. 0.452. Now I can come over here and do part 2, which is the horizontal equation of D equals V times T. This distance is my unknown variable. The velocity I know of 2, and again, we will be doing this in about 3 to 4 weeks. So this equation is actually the same exact scenario that you'll be doing in real life for your grade. T now is 0.452. Multiply those numbers, the distance right here, because what's going to happen is I'm going to give you a bullseye, you're going to put it on the ground, and where you land on the bullseye will determine your starting grade for this lab. This so happens to be 0.903 meter. Somebody last class period said, Miss Munson, do we need to go down to 0.903 or is 0.9 good enough? I was like, no, 0.9 is absolutely good enough. But when it comes to your lab grade, you might want to go down to the hundredths or thousandths place just to make sure that you are as accurate as possible. Okay? Now, let's go to question number 3. Question number 3, I see a theta. And remember, number one thing is, are you in degree mode? Okay? Don't forget to change it if needed. This one, I saw a lot of students like unsure when they turned in their homework. There's a tree. It says, how tall is this tree? How tall is it? I'm going to put a little question mark right here. How tall is the tree? Okay, now they did tell me that the tree actually is casting a shadow. Well, I don't know about you, but when I look at my shadow, I see it on the ground. There's the shadow of the tree. So the shadow is on the ground. Here's the ground. Now the sun, is shining on this tree. And it says that the elevation of the sun is 68 degrees. The angle of elevation on this is 68 degrees. Well, I know that when I look at this shadow in the tree, I see a right angle. Oh, yeah. Look at this. I see a triangle. If I cut it in half, remember how we started off with that pyramid and we cut the pyramid in half? The same thing for this situation. Whether you look at this half of the pyramid or you look at this half of the pyramid, it's still a right triangle. You know, when we did that and we had the person walking up the pyramid, it didn't matter, to be honest, if they were walking up this side or this side. It's still a half of a pyramid that formed, when we cut it in half, that right triangle. And what did we learn about right triangles? How to label them. Hypotenuse. Okay, here's my theta. It's actually 68 degrees. And my right angle in theta is my adjacent leg, and my leg that's left over is my opposite leg. Now, using this information, I can see that I'm actually looking for my opposite, and they gave me the shadow. The shadow is 14.3 meters. Like somebody got, I don't know, a measuring tape or something, and they measured the shadow on the ground. Now, because there's a theta involved, I'm going to have to SOHCAHTOA. And this is the A and the O, which means it's going to be our tan of our theta equals the opposite over adjacent, or the tan of 68 degrees equals, I don't know the O, and the A so happens to be 14.3. Multiply this side by 14.3, multiply this side by 14.3. Your opposite leg, or the height of the tree, is 35.5 meters. Pretty tall tree. Then, again, we need to keep up with those readings. I understand they may not seem super important, but what we read is to help add extra reinforcement to what we're learning in class. And sometimes we don't get to learn everything like in day one. For an example, this one right here. It says that my alien has a mass of 89 kilograms. Now, first thing is, we know mass is always in kilograms. If it's in grams, convert to kilograms, because the kilograms for mass is one of my 7 originals. Remember the parent units? That's one of them. And we should always be in kilograms. Now, it tells me that this alien is on Saturn, and the force is 929.16 newtons. Now, if you were unsure, because we haven't covered this yet in our notes, then number one, I hope you paid attention to your reading, or number two, you looked it up. You did a little bit of research, because we kind of got to do that now in college. You got to search out those answers on your own a little bit. Now, it says here, what is the acceleration due to gravity? It cannot be negative 9.81 because you're not on Earth, you're on Saturn. Okay, I'm going to pause right here. I'm going to come back to this question in just a moment, because I'm going to go to our notes right now, and then I'll come back and show you how to do that question. But if anything, I hope you use any resources that you have available. That's what I hope you did. Now, notes. We are going to cover a certain point of our notes today. We will stop. Remember, I just covered those 2 pages, which is on D2L. We will stop when we get to these cartoon characters right down here. I was in the back, and when we come in tomorrow, we're going to hit this part right here, and then we're going to hit the big G equation. You need to come in, and I was looking for my scale. I found my scale. I'll have my scale down here on the ground. You need to come in tomorrow. If you want to take off your shoes, you can, or you can leave your shoes on. You've got to stand on the scale tomorrow. Okay? No one else is going to know your math other than me, you, and Jesus. That's it. Okay? So tomorrow, you're coming and stepping on the scale. So I will make sure to have the scale ready for you to stand on. I only break it out for this one unit. So, it's a nice scale. It's not brand new. We've been using that scale for a couple of years, but it doesn't get used very often. We need to end up our notes today talking about the word weight and mass because a lot of people get those words confused. But in physics, they actually have a definition. So let's go ahead and let's start off our notes. We already know how to do that. We're going to copy it off of D2L. Let's start our notes here. Because that homework problem that I stopped at talked about the word force. Let's go ahead and talk about force. Hopefully you kind of looked already and did a little bit of reading over force, but here we go. Force. Force has a definition. The definition for force is going to be a push or a pull. A push or pull on an object. That's the definition of force. A push or a pull on an object. Pretty easy cheesy. Now force has a variable and we call it a big F. That's my shortcut, force. It also has an SI unit, which is a capital N for newtons. And that's what I had mentioned on our lab for that third equation. Now, force is a vector. And what does that mean? It has magnitude and direction. Because it's a vector, we can represent force in forms of arrows. And we are going to, starting next unit, talk about vector forces, but not just having 1 or 2 arrows. We might actually have 5 or 6 arrows on one object. So we're moving towards another step. We're going to take this up another notch. For an example, we know that 10 newtons west would be represented something like that. And 3 newtons north should be a smaller arrow, but 5 newtons southeast should be about half of the 10 newtons. It needs to be about half of that size, but yet pointing southeast direction. All right, because force is a vector. Vectors are represented by arrows. Now, the word net force is the sum. And you can find the sum by adding or subtracting. Pretty easy cheesy. We're going to do the same thing. If we have 6 arrows, we will add and subtract all of them until we get arrows at a right angle. And then we will SOHCAHTOA. So we're going to pull that info that we've already learned into this for our next unit. The word net force is the sum of all the forces acting on an object to help determine whether the object, it says here, whether the object is moving and in what direction. Of the object will end up going. Like, what is overall the sum of it's going to end up going? Like what's going to happen? Is it going to go northeast? Is it going to go east? Is it not going to move? Is it going to cancel itself out and move at a constant pace in the north direction? What's going to end up happening? Now, forces are broken into 2 different types of forces. Your force is either going to be a balanced or unbalanced force. And this is actually pretty easy cheesy vocab. If it's a balanced, which is also called an equilibrium force, forces are acting on an object that actually equal 0. They cancel out and equal 0 to produce a net force of 0 on an object. It produces a net force, the sum ends up being 0. Easy cheesy. pretty much. So it says, well, let's do a simple picture before we move forward. Let's imagine we have this big giant building and you're outside and I ask you to push with everything you have, every Newton inside of your body to push on that building. Well, you probably know this building's not made of cardboard. It's a firm, strong building. The building actually is pushing back on you with equal amount of forces. Oh, look at those vector arrows. They're about the same size. And what happens is they cancel each other out and they end up equal 0. What's happening? You're not moving, the building's not moving. You just don't have it in you. These forces are in equilibrium, but our equilibrium forces can be doing either at rest, like this, where they cancel each other out, no one's moving. You're pushing everything you have, but the building's pushing back on you. Now, if the building was stronger than you, or let me say it this way, if the building was pushing more force on you, because some of you are thinking, well, it's a strong building, it's probably pushing greater. If it was, it would push you back and you would fall back. So this building is not pushing any more than what you are pushing on that building. Because if it did, you would fall backwards. It would literally push you back. So when forces are in equilibrium, or what we call balance, they're either going to be at rest like this, or they're going to be maintaining a constant velocity. Let's go ahead and let's take a glance at what letter C is saying. For an example, over here, if they tell you, hey, we're going to take you out to the water, let's go out to Galveston Bay, and we're going to go shark fishing. But I don't want you to catch a shark. Your goal is to hold this pole in the water and do not let that bobber come up or go down. Well, obviously, we're going to put some food on the hook. But if you can maintain that bobber at an equilibrium position, you're going to get paid a lot of money. Because we want to see that when this shark or big giant fish starts to pull on that food, the hook, you are able to pull back with enough force to maintain that bobber at rest. So, for an example, this is at rest. Now, if you say, forget it, I can't do it, I really want this shark, and you pull up, well, now your force is stronger and you're not equaling 0. Okay, you're not in equilibrium or balanced. Let's look at another one. This is whenever it's not moving. But what if you're on a nice smooth highway at 3 in the morning, there's no traffic, no rush hour, and you are driving at a constant cruise control. Do not get me wrong. We have friction from the road. We have friction from the air resistance. It's trying to slow you down. But you literally put your car into cruise control. And you are moving, just like it says right here, at a constant velocity, maintaining your speed. So this example is kind of like asteroids in outer space. There's no friction, no air resistance, no gravity. So asteroids can go forever in light years, and they will continue to move forever. But here on Earth, we have to have cruise control. We have to have some energy. Now, unbalanced forces is obviously the opposite of what balance is. Balance means that it's at rest. And so unbalanced forces are acting on an object that are not equal to 0. They don't equal 0. What happens is they are going to produce a motion, whether it's a big motion or a small motion, in a certain direction that is the greater force. Alrighty? So we've got this super bumpy road, and there's all these rocks, and we have this little kid here trying to pull his wagon. And so as he pulls his wagon, he's at least strong enough to pull the wagon in one direction, 8 newtons, but all of this gravel and, rocks are pulling against him 5 newtons. So when we look at these vector arrows in opposite direction, he, yes, is overall, quote unquote, winning by 3 newtons to the right, but is all of his energy going into pulling that wagon? No. Some of his energy is fighting against all of this friction on the road, right? So that's messed up. But unfortunately, we live here on Earth, or maybe that's a fortunate. There you go. How about fortunate? Because, we like breathing. Now, what I'm going to do, so that way we can hit the section of notes where I want to hit today, I'm going to skip over this section. We can come back tomorrow. And I'm going to go to Newton's 3 laws, which is super easy cheesy. It will be on our next quiz, okay? But you learned this in middle school. Newton has 3 laws of motion. His first law is also called the law of inertia. Hopefully this is like, I remember this. I remember my 7th, 8th grade teacher. Now, this first law tells me an object at rest stays at rest. And an object in motion stays in motion. I hope this is coming back to you. At a certain constant speed, but in a straight line. That portion, the straight line, is going to come back to hit us second semester when we start talking about light and electromagnetic waves. Okay? So an object at rest stays at rest. An object in motion stays in motion in a straight line unless acted upon by an outside force. Now, the fact that we live on Earth, the force is going to be gravity and friction. Okay? And the definition for inertia is the tendency to resist change. Meaning, if you're at rest, you stay at rest. Your water bottle is going to sit at your table. It's not just going to magically get up. And because it doesn't magically get up, that means there's no ghost just going to stay there until the wind blows it down. Oh, that's a force. It's not a ghost. Now, the example here that they give us is, for an example, dishes at rest. Or what about your cell phone? I mean, your cell phone didn't grow legs and walk off. Somebody took it, or you put it down somewhere else and forgot about it. That's where it's at. It didn't just grow legs and walk away. It's going to remain at rest. Okay, I'm going to skip the next part so we can keep going. Newton's second law is actually an equation on the formula chart. No need to memorize it. F equals ma. Or the force of an object depends on the mass of the object and the acceleration that it's moving. Okay. For an example, we've got two examples over here. Let me go ahead and fill this in first before I keep skipping too much. Capital F, not lowercase, stands for force, and force is a Newton, named after Sir Isaac Newton. Lowercase m stands for mass. Please make sure it's in kilograms or convert if needed. Oh, like that King Henry. If it's in grams, then you need to convert it to kilograms. It must be in kilograms. A stands for acceleration, like we've already talked about, and that's meters per second square. Now we can talk about the practice problems. Example number 1. That's an easy one. How much force, question mark F, is needed to accelerate a car that has a mass of 1,300 kilograms, oh, perfect units, and it's moving at the acceleration of 1.5 meters per second? Here's my equation right here, F equals ma. I'm looking for the force. They gave me the mass in the correct units and acceleration of 1.5. I mean, pretty easy cheesy. There you go, not bad at all. Just like, I'm going back to our home, you can stay right there. I'm going to go back to our homework. Let's look at question number 4. They gave me the force, they gave me the mass, and I'm looking for acceleration on Saturn. F equals ma, or 929.16 equals 89 times a. Divide by 89, cancel, divide by 89. The acceleration of this alien, I don't know what it is, on Saturn, all right, is going to be blank, blah, 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 but wait a minute. It's going to have an SI unit of meters per second square because it's acceleration, okay? Meters per second square. But I'm going to take a glance at the next question. It says this alien so happens to have a twin brother who has the same exact mass over here. But he actually lives on Jupiter. So that means that Jupiter is a whole different planet, and it's not going to be negative 9.81. It's going to be a different number. And his force so happens to be 2,206.31 newtons between the ground and his feet. What is his twin's acceleration on Jupiter? Well, the force is a different number. The mass is the same number, and A. Divide by 89, cancel, divide by 89. Acceleration equals, and that's the twin alien who's on Jupiter versus the other twin who's living on Saturn. Different planet, different units. Different acceleration. They're definitely not the same acceleration on Earth because they're different from Earth. They're on a different planet. Alrighty, so back to our questions. It says over here is a frog. that starting from a resting position, or VI equals 0, because I know rest means VI, the frog has a mass of 0.5 kilograms, good units, no need to change it. And when it leaps, its acceleration for leaping is 3 meters per second square. What is the force? F equals ma, or F equals, look at this. They gave me extra numbers that I do not need. 0.5 times 3. Oops. Newtons. 1.5 newtons. Now, Ms. Munson, that's pretty easy cheesy. And those alien questions, those were pretty easy cheesy too. Okay, let's take it up a notch. Turn the page. We're almost done. We have these two kids who are on roller skates. They're actually in the center of the roller skating ring, and they're going to push off of each other. Because they have skates, what's going to happen? They're going to go in opposite direction. It says here the amount of time that they took to push off of each other was 1.2 seconds, T. Both of them starting from rest, VI is 0. Sometimes numbers are extra junk, sometimes they're important, okay? So let's keep going. What is the force, question mark F, of the smaller skater? So if I look at these two skaters, that has a bigger mass, that has a smaller mass. We are looking at this smaller mass skater. And we only want to know what their force is. This skater is going to have a different force than this skater. Why? Because they have different accelerations and different masses. Yes, sir?
Is it the force they're exerting or the force that they receive?
The force that they are exerting. Good call. We haven't got to Newton's third law, because that would be also then receiving. The action-reaction. Good call. So what is the force that that skater is exerting? Good call on that one.
2.5.
2.5?
Yeah.
Where'd you get 2.5 from?
On the after.
Oh.
Or not the force, but the acceleration they're exerting.
How'd you get the 2.5 on acceleration?
Because the force that they are exerting is transferred to the other person.
Okay. All right. Let's double check it. Let's do the math. I see what you're saying, but let's math it out just to make sure it's right. Number one, F equals ma. Did they give you the m of the smaller skater?
Yes.
Okay. Did they give you her a?
No.
No. Let's find the a. I'm going to call this now step 2. I'm going to have to work backwards first. A equals VF minus VI over T. Do I have a final velocity? Sure do. There it is, 3. Do I have an initial? 0. T, 1.2. 3 divided by 1.2? 2.4?
No.
Oh, close. 2.5. Pretty good. 2.5 meters per second square. Okay. Now, we're going to come over here. F equals the mass, which is 40. Let's multiply it by the acceleration of 2.5. That's where that number is coming from. That is opposite. I agree on that part. Now, multiply it by the 40. I have 100 newtons of force is what she is exerting on his hands right here. Now, his force is a different number because he has a different velocity or a different acceleration and a different mass. I'm listening.
So would our answer be the difference between the two? Or
No.
is that just a red herring?
Say it again.
Or is that just red herring?
Yeah, no, This is just to, throw you off. Yeah, No, you would have to go and find his force. The difference between the two would be this equation that you did outside on that lab. There you go. So there goes her force when she touched his hands. His hands is going to be a different force that he pushes on her because he's a different mass and a different velocity or different acceleration. The last portion here is Newton's third law. For every, and this is easy cheesy, for every action, you remember this from, sorry. Oops, sorry. For every action, there is an equal and opposite, reaction. For an example, as this little fishy swims through the lake, pond,
It pushes the water behind it.
there you go. The fish hits the water molecules, which is the action, but the reaction portion is the water hits the fish. You decide on what two portions are going to be acting with each other. For an example, you're walking along and you're at the zoo. Your feet are hurting at the end of the day. Well, that's because your foot hits the ground hits your foot back. So at the end of the day, your feet hurt. They're sore because you were hitting the ground and the ground was hitting your foot all day long as you walked around. The last two definitions is weight and mass. This is where you're going to come in tomorrow, and I'll just have this up on the screen. And tomorrow, you're going to put your number right here. Do you see that? In pounds. So you're going to stand on the scale tomorrow, and you're going to look at the number, and you're going to put that number here. Everybody's number is obviously going to be different. Now, we have two more vocab words, the word mass and the word weight. Those are two words that people kind of like accuracy and precision. Most people get those two words incorrect. Most people get these two words incorrect regarding physics. So the amount of mass you probably were taught in chemistry class is the amount of particles or matter in that object, right? How much mass is the amount of matter that object contains? Like how many atoms, how many compounds? It is measured in kilograms, and that's the reason why if we are in grams, then we need to convert it. Just like if you did that in the lab on Tuesday, you need to convert it to kilograms. Your mass is the total amount of stuff you're made of. Like how much skin and water and cells, all of that that's inside of you is your mass. That is not your weight. Your weight is a measure of the force of the gravitational pull. We so happen to live on Earth, and so for us, it's 9.81. Do you see how that answer or those questions with the aliens, they were on Saturn and Jupiter. They had different forces than if they were on Earth, because those are different gravitational pulls. So it's due to the amount of gravitational pull on the mass of your body. The key portion here for you to take away is that mass will never, ever, ever change. If you were to get in a spaceship and go to the moon, you would have the same mass. Your weight is determined by the amount of gravity pulling on you. Weight changes due to gravity. If gravity changes, your weight changes. Okay? So tomorrow, The scale will be on the floor. You need to get that number and write it down on your lab paper. Nobody needs to see it, okay? It's your personal number, but you will do the math tomorrow. Other than that, we are done.